n factorial d to the power n by dxn of x minus n to the power n. Okay. So these are the things. Then spherical harmonics, how we can use it. Then hypergeometric function, how can we use this? Then next is Hermite polynomial, which I was discussing by solving the Hermite differential equation. And you have your Hermite polynomial of degree 2m plus 1. And this graph I was explaining by evaluating h0, h1, h3, so on and so forth. And the value of these, which I was derived from Legendre polynomial. Then your generating function g is equal to e to the power 2xt minus t square is equal to summation n is equal to 0 to infinite hn t to the power n factorial. Then your recurrence relations. Okay, I was discussing a lot of recurrence relation with proof, and here only few. These are the Rodrigo formula, which I was discussing with the proof, and you can have you can refer it. Then orthogonality relation. Then your Lagrange polynomial. X d square y by dx square plus 1 minus x dy by dx ny is equal to 0. And you can solve it by the same method power series by having y dash, y double dash, and then your initial equation and your initial equation and your recursion initial equation and recursion equation, and from that case 1 and 2, so on and so forth, and solve this. Then Rodrigo formula and graph of Lagrange polynomial for L0, L1, L2, L3, L4. Then your generating function g is equal to e to the power minus xt by 1 minus t, 1 minus t by divided by 1 minus t, which is equal to n is equal to 0 to infinite ln t to the power n. Then your orthogonality relation, and you can have also orthonormality relation. Then Sturm-Liouville problem, and expansion of orthogonal function. Okay, and there is also associated Lagrange or associated Legendre and associated Legendre polynomial. You can also solve it, which I was discussing. Okay, there are some SAQs, and you can have you can go through it. Okay. Am I audible?
Yes, sir.
Okay. So very few people are left. I think only 8 people are there now. So what should I do? Shall I continue, or tomorrow we shall discuss the rest of the things?
Sir, discuss today, sir.
हाँ ठीक है. अभी तो सिर्फ 7 participant remained
10
here,
people, sir.
and your IGNU and your IGNU is
Sir,
also not
19
here.
students are there.
So now joined, many people joined. Okay, ठीक है. So ठीक है, we shall continue. Yesterday there are many people than today. Let us wait for 5 minutes. If more people will join, then we shall continue. Otherwise, we shall go discuss it tomorrow. Please mute yourself, then we shall start. Mute yourself. Or somebody mute. Okay, thank you. So, you might have come across this Fourier transform and Laplace transform. Okay. Is the screen visible?
Yes, sir.
You know, for a Fourier series, and in complex form, you can write a Fourier series in such a form that is fx is equal to a0 summation n is equal to 1 to infinite n cosine of 2 pi nx by capital T plus bn sine of 2 pi nx by capital T. And your it is a periodic function, so we can write f of x plus t is equal to fx, where after time interval t it repeats itself. So your Fourier coefficients or Euler formula, which is popularly known, uh, have the form like a0, an and bn, and your a0 is equal to, in Euler formula, 1 by t integration minus t by 2 to t by 2 f of x dx, and your an will be 2 by t integration minus t by 2 to t by 2 fx cosine of 2 pi nx by t dx, and your bn will be 2 by t integration minus t by 2 to t by 2 f of x sine of 2 pi nx by t dx. And in you can have your cosine and sine function in an exponential form in a complex format, that is e to the power ix is equal to cos x plus I sin x, and you can write e to the power minus ix is equal to cos x minus I sin x. And your cos x can be written as e to the power ix plus e to the power minus ix by 2, and sin x can be written as e to the power ix minus e to the power minus ix by 2i. So your original expression fx can be written as a0 plus summation n is equal to 1 to infinite n e to the power n pi ix by t plus e to the power minus 2 n pi by uh, minus e to the power minus 2 n pi x by t by 2 plus bn e to the power 2 n pi ix by t minus e to the power minus 2 n pi ix by t divided by 2i. So you can write your fx is equal to a0 plus summation n is equal to 1 to infinite an minus ibn by 2 multiplied by e to the power your 2 n pi ix by t plus an plus ibn by 2 e to the power minus n pi ix by t. So now the coefficient C0 can be defined as A0 and Cn as An minus Ibn by 2, where An, Bn are Fourier coefficients, and your Dn is equal to N plus Ibn by 2, where An, Bn are Fourier coefficients. So you can write the modified expression. Your f of x is equal to C0 plus summation n is equal to 1 to infinite Cn e to the power In pi ix by t plus summation n is equal to 1 to infinite dn e to the power minus 2n pi ix by t. And you can write your c minus n is equal to dn. So you have your n is equal to 1 to infinite dn e to the power minus 2n pi ix by t is equal to summation n is equal to 1 to infinite c minus n e to the power minus 2n pi ix by t is equal to summation m is equal to minus 1 to infinite cm e to the power 2 n pi ix by t is equal to summation n is equal to minus 1 to minus infinite cn e to the power 2 n pi ix by t. So the general form of fx can be written as summation n is equal to minus infinite to infinite cn e to the power 2 n pi ix by t. And your dn can be written as c of minus c subscript minus n 1 by t integration minus t by 2 to t by 2 f of x e to the power 2 n pi ix by t dx where n is greater or equal to 1. And in complex form, you can write the Fourier coefficient Cn is equal to 1 by t integration minus t by 2 to t by 2 f of x e to the power minus 2 n pi ix by t your x dx. So, for periodic functions, your Fourier series is very much important to use in physics and engineering. But often we come across some situation in which we have to deal with it, aperiodic function which are not periodic or which are not in the form f of x plus t is equal to f of x. So to extend the Fourier series solution to aperiodic function, we use Fourier transform. So please see in the screen a rectangular periodic pulse with period t shown in A, and the same pulse with a large t shown in B, and in your as the t made infinitely large, there is only one pulse giving an aperiodic function as shown in C. So an aperiodic function fx as the limit of a periodic function f of t is its period t tends to infinite. So you can write f of x is equal to limit t tends to infinite f subscript capital T, which is a function of x. And if the original periodic function contains a finite number of finite discontinuities in one period, the function obtained after taking the limit t tends to infinite would possess a finite number of finite discontinuities in the whole interval minus infinite smaller than x smaller than infinite. So by expanding a periodic function, we can solve it. So let us start with complex Fourier series of periodic function and take the limit t tends to infinite. You know a general periodic function f of t with period t can be written as f of t is equal to summation n is equal to minus infinite to infinite Cn e to the power I k n x. And this can be written as 1 by t summation n is equal to minus infinite to infinite e to the power I k n x integration minus t by 2 to t by 2 f of u e to the power minus I k n u du, where your k n is equal to 2n pi by t and u is the variable of integration. You know del k is equal to kn plus 1 minus kn is equal to 2 pi by t. So we can replace 2 by t by del k by pi. And our f of tx can be written as 1 by 2 pi summation n is equal to minus infinite to infinite minus k. F of t can be written as 1 by pi integration n is equal to f of t can be written as 1 by 2 pi integration n is equal to minus infinite to infinite your delta k e to the power I k n x integration minus t by 2 to t by 2 f of u e to the power I k n u du, which can be written as 1 by 2 pi summation n is equal to minus infinite to infinite f of kn del k, where your f of kn is equal to integration minus t by 2 to t by 2 f of u e to the power I kn x minus u du. So we allow t to tend to infinite. So here three things may happen. First, the limit of all integral become minus infinite to infinite. Second, 1 by t tends to 0. And the third, the difference del t is equal to 2 pi by t between successive values of kn also becomes smaller and smaller. And you can deal the situation only if the integration minus infinite to infinite modulus of fx dx is smaller than infinite. So you can write this where fx is equal to limit t tends to infinite ftx. Assumed that this condition is satisfied, we are now justified in taking the limit t tends to infinite for f of t, which is a function of x, and the left hand side can be replaced by f of x after taking the limit t tends to infinite. In the integral, in the right hand side, we can replace kn by k and summation over n from minus infinite to infinite by integration over k from minus infinite to infinite. So we can note that these limits are consistent with the definition kn is equal to 2n pi by t, through which we have made the transformation from n to k. So we have your f of k is equal to integration minus infinite to infinite f of u e to the power I kx minus u du. And f of x is equal to 1 by 2 pi integration minus infinite to infinite integration minus infinite to infinite f of u e to the power I kx minus u du dk, which is equal to 1 by 2 pi integration minus infinite to infinite e to the power I kx dk integration minus infinite to infinite f of u e to the power I ku du. So your gk can be written as 1 by 2 pi integration minus infinite to infinite f of u e to the power minus I ku du is equivalent to 1 by 2 pi integration minus infinite to infinite f of x e to the power minus I ks dx. So your f of x can be written as integration minus infinite to infinite gk e to the power I kx dk. And for regions of symmetry, we multiply both fx and gx by 1 by root over of 1 by 2 pi instead of having a factor 1 by 2 pi in only one function. So you can define Fourier transform as follows: f of x is equal to 1 by root over of 2 pi integration minus infinite to infinite gk e to the power I kx dk, and gk can be written as 1 by root over of 2 pi integration minus infinite to infinite f of x e to the power minus I kx dx. And the function gk is called Fourier transform of fx, and fx is called the inverse Fourier transform of gk. So two integrals differ in form only in the sign of the exponent. In your Fourier transform, the sign of the exponential part is positive, e to the power I kx, and in inverse Fourier transform you have your e to the power minus I kx. Okay. The quantity k is continuous analog to the integer n, and so the set of discrete coefficients has become a continuous function gk. The sum over n has become an integral over k. We can state this result in form of Fourier integral theorem, which is very important. If a function fx possesses no more than a finite number of finite discontinuities, and if the integration minus infinite to infinite fx dx is finite, then it can be expressed in form of an integral that is shown in the screen, fx and gx with the coefficients 1 by root over of 2 pi. The Fourier series of a periodic function tells us which frequencies or wave vector of sinusoidal wave we should superimpose, and what the amplitude of each wave should be, so that we get the original function. Similarly, the Fourier transform of a function tells us which wave at what frequencies and what amplitude should be combined to get the original aperiodic function. Okay. The only difference is that whereas it requires discrete frequencies or multiple or harmonics of the frequency of the periodic function to generate a periodic function, you require a continuous range of frequencies at all frequencies to generate an aperiodic function. So here are some examples. Fourier transform of a single square wave. Whenever a function has a discontinuity, its Fourier integral at the point equals the average of the left hand limit and the right hand limit of the function at that point. Then you have the Dirichlet discontinuous factor. Integration 0 to infinite sin k cos kx dk by k is equal to pi by 2 when modulus of x is smaller than 1, is equal to pi by 4 when modulus of x is equal to 1, and is equal to 0 when modulus of x is greater than 1. Then Fourier transform of the electric field in a radiated wave shown in the screen. Then you can obtain the Fourier transform of the function ft is equal to 0 when t is smaller than 0 and is equal to e to the power minus lambda t when t is greater or equal to 0 and lambda is greater than 0. And your fx is equal to x when 0 is smaller than x, smaller than 1, and 0 otherwise. So you know, in Fourier series, we have dealt with the odd and even functions. The pair of Fourier sine transform represent odd functions and are known as Fourier sine transform and can be represented as f subscript s, which is a function of x, is equal to root over of 2 by pi integration 0 to infinite gsk sine kx dk, and your gs is equal to root over of 2 by pi integration 0 to infinite fs sine kx dx. Similarly, the pair of Fourier cosine transform representing even functions are known as Fourier cosine transforms and are represented as fc x is equal to root over of 2 by pi integration 0 to infinite gc cos kx dk, and your gc is equal to root over of 2 by pi integration 0 to infinite fc cos kx dx. You know, Dirac delta function peaks at a point, and one-dimensional Dirac delta function is conventionally defined as delta x is equal to 0, where x is not equal to 0, and your integration minus a to b delta x dx is equal to 1, where a comma b is greater than 0. And if delta x minus x dash is equal to 1 by 2 pi integration minus infinite to infinite e to the power I x minus x dash y dy is popularly known as integral representation of the Dirac delta function. Fourier transform obeys linearity, time shifting, frequency shifting, time scaling, time reversal, differentiation, integration, and convolution, and is shown in the screen. If you do not understand it, then I can explain. And your multiplication Duality, modulation are also properties of Fourier transform. And you might have come across Parseval's theorem, that is if f(1), which is a function of t, Fourier transform g1, which is a function of omega, and f2t, Fourier transform g2, which is a function of omega, then integration from minus infinite to infinite, f1, f2 star dt is equal to 1 by 2 pi integration over minus infinite to infinite g1, g2 star d omega, where f2 star and g2 star are complex conjugates of f2 and g2 respectively. Then your Laplace transform. Laplace transform are widely used in various areas of physics to solve differential equation. The Laplace transform fs of a function ft is defined as fs is equal to integration 0 to infinite e to the power minus st f of t dt. And you can write it as shown in the screen. Fs is equal to L over in the square bracket f of t. And the inverse Laplace transform can be represented as f of t is equal to L inverse f of s in square bracket. Like Fourier transform, Laplace transform obeys linearity, time space shifting, frequency shifting, known as a fast shifting theorem, time scaling, time reversal, differentiation, integration, convolution, modulation, and initial value theorem can be represented as if fs is strictly proper fraction, then according to the initial value theorem, limit t tends to infinite f of t is equal to limit s tends to infinite s fs. And the final value theorem is if the final value exists, then the theorem states that limit t tends to infinite f of t is equal to limit s tends to infinite s f of s. And you have the Laplace transform of elementary functions shown in a tabular form. If the function is a constant represented by c, then fs is equal to c by s. And if the function is in a form of t to the power n, then Laplace transform fs is n factorial by s to the power n plus 1. If the function is in e to the power ct format, where c is a constant, the Laplace transform fs is equal to 1 by s minus c. Similarly, if ft is equal to cosine function cos pt, then its Laplace transform fs is equal to s by s square plus p square. And if it is in a sine function, that is f of t is equal to sine pt, then fs is equal to p by s square plus p square. If it is a hyperbolic function, so your f of t is equal to cos hyperbolic pt, then Laplace transform fs is equal to s by s square minus p square. And your if it is ft is equal to sine hyperbolic pt, then f of s is equal to p by s square minus p square. And you remember this to solve the problems. Then you can have some examples by which you can well acquainted with how to use Fourier transform in different applications. One of these is solve the wave equation for amplitude of vibration of an infinitely long vibrating string given by del square y by del x square is equal to 1 by v square del square y by del t square by assuming the initial condition y x comma 0 is equal to f of x. You can also solve a problem of diffusion of certain quantity of salt in water by supposing at time t is equal to 0, salt of mass m is introduced at a point x0 in water flowing in long and narrow pipe. You can also obtain the concentration of salt rho at a later time t that satisfy the one-dimensional diffusion equation del rho by del t is equal to d del square rho by del x square by using the initial condition. Then one-dimensional forming age equation for diffusion of neutrons slowing down in some medium say equal to del Q by del tau, where Q is the number of neutrons that slow down falling below some given energy per second per unit volume, and tau is the Fermi age and is a measure of energy loss. There are some other applications. You can convert a differential equation into algebraic equation by method of Laplace transformation. You can solve algebraic equation by Laplace transformation. And you can obtain inverse Laplace transform of algebraic solution, which will give the solution you want. Okay. So you go through these, and if you have any doubt, you are free to ask me.
Sir, share the previous PDF.
Yes, I shall share. Some of any of your student, please have a hi to my WhatsApp so that I can send
Yes, sir.
or
Sir, we have a group. If you will tell, I will join you.
I am giving my WhatsApp number. I think I am not in that group.
Yes, sir. You are not there in group.
So
Vivek sir was there.
this is my
If you
WhatsApp
say,
number.
he will say.
If this is my already the course is going to be completed, so you don't need to add me in
Sir, you're not audible.
the my WhatsApp number I have sent in the in-call messages. Anybody, please give
Sir,
a
if you have Vivek sir number, you can say him to add you.
the course is going to be completed within a day or two. So no
Yes,
need
sir.
to just anybody has a hi to me or had
Okay, sir. You say your number. I will message you.
and you can circulate it among other students. Okay.
Yes, sir.
Even sir already shared his number in the chat group.
Okay,
Last
okay.
section.
Anybody take your time and have a message.
Add
That's it.
sir, add, add sir numbers on the group.
Yes, yes.
Okay. So let us have the next class tomorrow.
Okay.
Thank you.
Hello, sir. Sir, I have added you in the group
Okay.
physics squad.
Okay.
Just accept the invitation.
अरे भाई किसी को समझ में आ रहा है वो सर क्या पढ़ा रहे? सर तो पूरा ऐसे ही बुक पढ़ रहे हैं।
Like a GK book.
हाँ, इससे तो कैसे चलेगा? हमेशा ऐसे ही करते।
Anyone have a July section assignment answer?
कुंज पब्लिकेशन करके कुछ है, उसमें आप जाके वो परचेज कर सकते हैं। एक का वो 50 रुपीज करके कुछ लेते हैं।
हाँ वो परचेज किया था, उसमें आंसर गलत था।
अच्छा, मैंने तो पूरा नहीं ले।
इसलिए ट्रस्ट नहीं आ रहा है। कितना खरीदूंगा उसके बाद फेक आएगा, इसलिए।
भाई चैट जीपीटी यूज करो।
क्या क्या?
ଚାଟ୍ ଜିପିଟି ରେ ଆସୁଛି ଆନ୍ସର।
या
ଭାଇ ତମେ ଲେଖିଲଣି ଆନ୍ସର ଲେଖିଲଣି?
हाँ
ଆଁ, ମୋ ନମ୍ବର ଟା ମୁଁ ସେୟାର କରୁଛି, ମତେ ଟିକେ ମେସେଜ କରିବ।
ठीक अच्छे
ଏଇଠି କହିବି। ଭାଇ
हाँ हाँ
ହ୍ୟାଲୋ,
हाँ हाँ
7684 7684 900
हाँ
552।